So, we will continue our discussion on IC engine. Today we will discuss about Otto, diesel and dual cycles. So, but we would like to discuss a few important issues that we could not discuss in my last lecture. So, before I go to discuss about Otto, diesel and dual cycles, I will recapitulate those, I mean, which are very important before I we go to discuss about Otto cycle, diesel cycle and dual cycles, because when we will discuss about Otto, diesel and dual cycles, of course, we need to know what is the work output from the engine, and then we have to quantify the efficiency. And of course, in as I said you that Otto, diesel and dual cycles, that I will today I will tell that, but in case of SI and CI engine, we have seen that whether it is 4 stroke or 2 stroke, we are having a continuous change in pressure and volume. So, whenever we are having change in pressure or volume, then of course, thermodynamic states of the working substance will be changed. So, whenever the thermodynamic state of the working substance is getting changed, then we need to map the thermodynamic states at the end of each and every strokes in a thermodynamic plane, and probably the change in pressure and volume, rather the change of thermodynamic states is approximated by the air standard cycle. So, in case if it is an SI engine, then I mean whether if it is a 4 stroke SI engine, this is an air standard cycle, but this is approximated by an air standard cycle which is known as Otto cycle. Similarly, in case of a 4 stroke CI engine, again we need to compare, rather we need to map those changes of thermodynamic state, I mean using a air standard cycle, and probably diesel cycle is also an air standard cycle. I mean whenever we are whenever we are interested to calculate the efficiency, work output, and also the change in pressure and temperature at the end of each and every stroke, we need to again follow air standard cycle, and this is the air standard cycle which is approximated. Diesel cycle is an air standard cycle which is used to map the thermodynamic states, a change in pressure and volume of a 4 stroke CI engine. So, before I go to discuss in detail about this Otto, diesel and dual cycle, just I would like to recapitulate very important points which are we can say that engine operating characteristics, rather that whenever we are, because internal combustion engine it is similar to heat engine. So, it is very important that work is only the output. So, we need to quantify that the output work from engine. So, we need to know how we can calculate work, and probably last lecture we have discussed about the change in pressure and volume in a 4 stroke engine, and probably that diagram whatever I have discussed in my last lecture, that is known as indicator diagram, or sometimes it is known as valve timing diagram. So, from this diagram we need to quantify the work output from the from that cycle, I mean whether it is Otto cycle or diesel cycle 4 stroke engine, because we have seen that in a 4 stroke engine we are having only one power stroke versus there are 3 idle strokes. So, we will get work output only from the power stroke, rather for 3 different other strokes we need to supply work or supply energy from the flywheel. So, that is why we need to quantify a few important terms which are related, rather which are directly related to performance of an internal combustion engine. So, initially I will discuss about the work. What is work? So, this is very important. What is work? That is, work is only the output from a heat engine or internal combustion engine, right? It is very important in a reciprocating IC engine. So, work, this is very important. So, work is the output from a reciprocating IC engine, because whenever we are having work is the output, work is only the output, rather work is the output from a reciprocating IC engine, because we have seen that in a 4 stroke engine we are having a reciprocating motion of the piston, and somehow we are converting that reciprocating motion into the rotary one using a crank and connecting rod mechanism. So, we are getting some amount of work inside the cylinder, and maybe it is not always possible that whatever amount of work we are getting inside the cylinder is not transferred to the crankshaft. So, maybe the amount of work we are getting at the crankshaft is less than that produced inside the cylinder. So, we will discuss all those issues. So, work here is the output from internal combustion engine. Now, question is how work is produced. As I said you that if I try to recall again, say that the diagram we have drawn in the last lecture, that is known as valve timing diagram or indicator diagram, PV. So, if it is atmospheric pressure, so if it is P atm, then we have seen that we are having, this is V TDC and we are having V BDC. So, this is volume and this is V BDC. So, we have plotted that so this is the process and so 1, 2, 3 and if I tell it 4.4. So, this is very important that whenever this is known as indicator diagram or sometimes it is known as valve timing diagram. We have discussed in details that opening and closing of different valves, I mean 2 different valves, that is intake and exhaust valves, and we have identified that there is a small time period over which both the valves are remaining open. This is known as valve overlapping region. So, this is valve timing diagram. Question is, so we have seen that in a 4-stroke engine only power stroke is a stroke from where we are getting power, and for 3 other remaining stroke we need to supply power from the flywheel. So, how whenever we are having we are getting power output, then how we can quantify, rather why work is produced from the engine cylinder, because of course we have to have work output from the engine, otherwise how I can drive auto 4-wheelers, 2-wheelers, whatever it is. And if I see, if I draw the schematic of a internal combustion engine again, so we have seen that if this is the TDC, top dead center, sometimes it is known as inner dead center and this outer dead center, BDC, and this is piston. I am not going to draw the piston ring again. So, if this is the engine cylinder, so what is happening? We are having reciprocating motion of the piston inside the cylinder. So, we are having a reciprocating motion, piston is coming and piston is travelling from TDC to BDC, again going back to TDC, and we will have a suppose we will have a piston rotary motion. So, this crank and connected rod mechanism, we have a rotary motion. So, this is the rotary motion of the crank, and whenever there is a compression stroke, of course, we need to supply energy, because we need to travel, we need to allow piston to go back from BDC to TDC, and air fuel mixture in case of SI engine and only fresh air in case of a CI engine will be compressed. And before piston reaches at TDC, we will discuss again while discussing the Otto and diesel cycle, rather while we are mapping the change in pressure volume using an air standard cycle which are known as Otto and diesel cycle for SI and CI engine respectively, that there will be a few approximations, and we will discuss those approximations are not very are not bad approximations. So, whenever piston is coming back from BDC to TDC, and probably in case of SI engine we need to switch on spark plug, which is an external agent which initiates combustion, or if it is a CI engine, then we are utilizing the high pressure temperature of the compressed air itself, and whenever piston is reaching closer to TDC, we have already the high pressure temperature of the compressed air, and the moment when we are spraying fuel, rather we are injecting fuel through a fuel injector into the cylinder, it will automatically start combustion. So, whenever combustion is there, that means we are already we have compressed air and fuel or only fresh air. Then if we ignite either through a spark plug or we are utilizing the high pressure temperature of the compressed air itself, then again combustion will start, and there will be a huge pressure and temperature rise. So, that high pressure will try to create a thrust on the piston face, and piston face will try to come back from TDC to BDC, that is known as power stroke. So, because of the generation of high pressure that is acting on the piston face, so there will be a force acting on the piston face, and because of that force piston will come back from TDC to BDC. From there we can quantify work, because there is a really whenever piston is coming back, so that means a force is generated, and that force due to high pressure, of course either high pressure because of combustion, and that force is essentially responsible for the work output from our internal combustion engine. So, force, this is very important, force due to high pressure because of the combustion, force due to high pressure because of the combustion is responsible for work output from a reciprocating IC engine. That means force is acting on the piston face, and because of that piston travels. So, because of the force being applied on the piston face, piston moves a distance in the cylinder, and results in the work output, results in the work output. This is very important, that because of this force acting on the piston face, piston will traverse a distance in the cylinder, and because of that we can have work output. That means I can write that work, if work is W, and then if I integrate, if F is the force and piston is having an instantaneous rather small distance through which, very infinitesimal distance through which piston is traversing, dx, then W is equal to F dx. So, F is equal to force on the piston face, that is essentially pressure developed into area of the piston. So, where A is the piston area. So, if I write this, then work output W is equal to P A dx, this is very important, P A dx, and x is the distance through which piston moves, where dx is the distance, this is distance the pistons moves. So, this is very important. Now, so this is the work output from engine that we are getting. Very importantly, this see A into dx, this is essentially dV, this is volume, that is a differential volume displaced by the piston. So, dV is the differential volume displaced by the piston, right. So, W is equal to P dV work that we are getting. So, if it is P dV work, then from the that indicated diagram, that is what we have drawn from here, that I know the change in volume. So, essentially area under the process curve from the indicator diagram or valve timing diagram, we can directly measure the work output from engine. So, if I calculate the area under the process curve, because as I said you that while we are having inlet, exhaust and compression stroke, we need to supply work to the engine cylinder, to the piston, while we are getting work output from the piston during the power stroke. So, since it is PDV work, we can calculate work from the indicator diagram, because this is area under the this is very important, this is because this is the area under the process curve. So, very important that we have to calculate that what will be the total area, because it is always advisable that we should quantify PDV. So, this is the work output from the reciprocating IC engine, because now we can directly get it from PV diagram, because area under the process curve will give us the work output from the engine. It is very important. Importantly, see, sometimes very often that not sometimes very often engines are multi-cylinder, very often engines are multi-cylinder, very often engines are multi-cylinder, very right. So, since it is an very we need to get huge high work output from the engine. So, it is quite common that we have a multi-cylinder engine. If that is the case, so it is convenient to analyze engine cycle per unit mass, since it is very often that we need to get huge power output. So, it is convenient to express to analyze the engine cycle. So, it is convenient to express the engine cycle. Since engines are very often multi-cylinder, it is convenient to express engine cycles per unit mass of the gas, per unit mass of the working substance of gas rather, or I can write working substance, because it is only air fuel mixture in, it is only air in case of a CI engine, but it is air fuel mixture in case of a SI engine. So, working substance I can write within the cylinder. Within the cylinder. So, now to do so, what is done, that V, and to do that this V is replaced by specific volume, that is capital V by M, specific volume V, and work W is replaced by the specific work output, by the specific work output, by the specific work output. That means small w, that is specific work output from the cylinder, will be P into dV. This is very important, rather I can write as P into dV. Since engines are very often multi-cylinder, it is convenient to analyze engine cycle per unit mass of the working substance of gas within the cylinder. Then because we are having multi-cylinder engine, so the total work output will come from different cylinders. So, in that case it is always convenient that how much amount of work that we supplied to the engine, or how much amount of fuel air we have supplied to the engine, and then that volume V is replaced by the specific volume, and works will be the specific work output. So, specific work output will be equal to P small dV, and this is very important for the multi-cylinder engine. Fine. Again I am telling this is the work output from engine, and we can directly get it from the PV diagram only by calculating the area under the process line. And we need to know that, again I am repeating that intake, exhaust and compression stroke which absorbs work from the cylinder. On the other hand, power stroke provides work to the engine cylinder. So, from there we can, I mean, whether it will be added or it will be subtracted, that is quite straightforward, and from there, from the area under the process line PV diagram, we can calculate the work output. Okay. So, now this is the work output, very important. Very importantly, that is what I was telling, that maybe so the specific work is equal to the area under the process line on PV coordinate, that is what I am telling, very important, that the specific work output is equal to the area under the process line on PV coordinate on PV coordinates in indicator diagram. Right. So, specific work output is equal to the area under the process lines on PV coordinates in a indicator diagram. Fine. Next, I would like to discuss that again, if I draw the engine cylinder, this is very important. So, if I draw the engine cylinder, suppose this is this piston and this is TDC, this is BDC, and piston will move in this direction. So, we may have air supply. I am not going to draw the supply line of air, exhaust manifold, all those things, but this is the indicator, this is the engine cylinder. Whatever amount of work we are getting inside the engine cylinder, so work output, very important. So, that is work generated, work or rather work developed is very important, work inside the combustion chamber. So, work inside the cylinder is called indicator diagram, because P represents the presence of the cylinder combustion chamber, then whatever areas, so then W into P dV. So, if I have calculated specific work output will P into dV, if this P is the pressure inside the combustion chamber. So, this is the pressure inside the combustion chamber, so this is the pressure inside the combustion chamber, then work output using this expression, or if I try to get it from the area under the process line PV coordinate on the PV coordinates from indicator diagram, that is if I try to calculate work using this expression, or even if I try to calculate work from the area under the process lines on PV coordinates in a indicator diagram, this is the work inside the cylinder. So, this is the work inside the cylinder, right, and this work is known as indicated work. So, this work is known as indicated work, very important. So, that means work what we are calculating using this expression P dV, or else if I try to calculate work under the area of process lines PV on process lines on PV coordinates in an indicator diagram, that will be the indicated work. That means the work available at the crankshaft is lesser than the work inside the cylinder, This is very important, because this is quite obvious, because work available at the crankshaft is always lesser than the work inside the cylinder. That means because of what? Maybe we are getting work output from the engine cylinder is indicated work, because P is the pressure inside the combustion chamber. So, if I try to calculate work using that formula, that will be indicated work, but the work available at the crankshaft is always, the work available at the crankshaft is always less than the indicated work because of some parasitic loads. This is because of frictional effect and other parasitic loads. This is very important, we need to know other parasitic loads. What are the parasitic loads? So, parasitic load different, because we should know, this is very important, because parasitic load, what do you mean by, we should know about it, because parasitic loads, that means when you are having, suppose we have a 4-wheeler. So, always we are we always try to find out comfortable zone. So, maybe we need to insert an AC, air conditioner. So, to run that air conditioner, again we need to borrow work from the engine cylinder. On the top of that, yesterday I have discussed that we need to have a proper cooling system. So, cooling should not be so stringent that the temperature will reduce drastically, and in that case efficiency might drop, other efficiency should drop. On the other hand, we should also have a proper cooling, otherwise lubrication system will burnt off, there might be a generation of thermal crack and failure of different valves, all those things. So, again that should not be the case. So, we need to have a proper cooling of the engine cylinder. That means, if we need to have proper cooling, it may be of air cooling or water cooling, that is what we have discussed. In case of a water cooling system, we need to supply water, and for that it will be water should be supplied to in the cooling water jacket. From there again it will be taken back to the radiator using a centrifugal pump, and to run that centrifugal pump we need to connect one V, that pump we need to connect using a V belt pulley with the crankshaft. That means, whatever amount of work is generated in the engine cylinder, a part of the work is taken to run all those things. We need to run air conditioner, we need to operate continuous cooling system, maybe lubrication system. For that, that is air conditioning, AC, then cooling system, then lubrication system. For those we need to supply work, because we need to run all those. So, these are known as parasitic loads. That means, very important, that means work available at the crankshaft, work available at the crankshaft is known as brake work, WB. So, W brake is equal to W indicated. I am writing the specific work available at the crankshaft is known as brake work, and that will be W indicated minus WF. So, this is indicated work, and this is very important, this is the specific work lost, the loss of work due to friction and other parasitic load. So, brake work is always less than indicated work by an amount which is equal to the loss of work due to frictional effect and other parasitic loads. Fine, it is very important. So, this is very important, that what is the brake work, what is the indicated work. Since the work available at the crankshaft is always less than the indicated work, we are defining one efficiency which is known as mechanical efficiency of the engine, which is known as, we will discuss about thermal efficiency, but mechanical efficiency of the engine eta m, which is defined, because brake work is the work that we are getting at the crankshaft. So, that work is responsible to drive to run the wheel, and because of what we can drive from one place to other place, but actually the work developed, the work produced inside the cylinder is the indicator work, which is greater than the brake work. So, this mechanical efficiency is defined as a ratio of brake work to the indicated work. So, this is known as mechanical efficiency. Very good. Now, we will discuss about a few things that again I told you that that work can be obtained from the indicator from the process lines on PV coordinates in the indicated diagram. As I said you that what is the gross indicated work, because gross indicated work is the work. So, we are getting work output, the work we are getting only because of the power stroke. For 3 other remaining strokes in a 4-stroke engine, we need to supply work to the crankshaft and we are getting it from the flywheel. So, from there we can easily calculate what will be the net work output from the engine, fine. So, this is very important, that what is the work and mechanical efficiency, that is what we have defined. Now, we will discuss another important issues, that okay fine. So, we have discussed about the work and what is, so if we need to calculate pump work, then easily I can calculate, because as I said you that if I go back to my previous slides where I have drawn the indicated diagram, see what is the pump work, intake and exhaust stroke which absorbs work. So, if I try to calculate, so this is the intake stroke 1 to 2 and this is the exhaust strokes 4 to 1. So, this area, if I try to give this area B and C, suppose if this is B, so this is B, total is B, this is A and this is C. So, B is the work where we need, this is called pump work, that is we are absorbing work, where A is the work which is produced, that is the work we are getting from the gross indicated work. So, sometimes there might be a case that the intake is taken, intake is introduced, the intake process is conducted even at a pressure which is higher than the atmospheric pressure. So, that issue we will discuss maybe I mean in one of our subsequent lectures, but for the timing we should know that intake, exhaust and compressions for which we need to absorb energy or rather absorb work, while in case of a power stroke we are getting power work from the engine cylinder, and that we can get from the process line, that is area under the process lines on PV coordinates in a indicated diagram. So, next we will discuss about, so we have discussed about the work output. Now, we will discuss about another important thing that is very important, I mean very another important term in the context of engine operation, that is known as mean effective pressure, very important, that is known as mean effective pressure. Mean effective pressure. So, this is known as mean effective pressure. So, what is the mean effective pressure? We have seen, if I recall, so if I go back to the actual PV diagram, we have seen that the pressure inside the cylinder is changing continuously, it is not a fixed. So, pressure and volume rather it is a continuously changing, right. So, during a cycle, pressure inside the cylinder is changing continuously. It is very important. So, pressure is continuously changing. So, that integral of PdV it is not so easy to calculate. So, we need to take help of a computational method, rather we can invoke an idea of mean effective pressure, so that an average or mean effective pressure we can define. So, W mean specific work output is equal to P into dV. P is the pressure inside the cylinder which is continuously changing during a cycle. So, it is not so easy to calculate instantaneous pressure inside the cylinder, and for that we need to invoke the computational method. So, instead of invoking computational method, we can define the concept of mean effective pressure, so that we can define the mean effective pressure, rather we can introduce mean effective pressure, which is known as MEP. So, we can define mean effective pressure, that means we are introducing the concept of mean effective pressure such that the specific work output can be written mean effective pressure into delta V, change in volume. That means mean effective pressure will be W by delta V. So, if I write instead of writing specific quantities, if I write in the total, then W by capital V, where delta V is essentially V TDC minus V BDC minus V TDC. So, change in volume during one cycle. So, here W is the work on cycle. So, here W is the work of one cycle, right. Then W is the specific work of one cycle, this is specific work of one cycle, and delta, rather small capital V, or this Vd I am writing that Vd is equal to displacement volume, this is displacement volume. So, now this is very important, work of a one cycle, we can introduce the concept of mean effective pressure only to get out, only to relief, to get relief out of calculating the instantaneous pressure inside the cylinder, because pressure inside the cylinder is changing continuously. So, if you would like to obtain pressure at a given instant is not so easy, we have to invoke the computational method or computational treatment is required. Instead of doing so, we can introduce the concept of mean effective pressure, which is defined as, so the specific work output will be equal to mean effective pressure in the change in volume delta V, that is V VDC minus TDC. From there I can calculate mean effective pressure. So, from there I can write mean effective pressure is equal to W by delta V. So, if I would like to calculate break mean effective pressure, that is only BMEP, that will be equal to break power by change in volume, or if I would like to calculate indicated mean effective pressure, that is W indicated divided by change in volume. So, I know the change in volume. So, this is break mean effective pressure, and this is indicated mean effective pressure, right. So, this is indicated mean effective pressure and this is break mean effective pressure. So, BMP and IMP we have calculated. So, this BMEP will be equal to IMEP minus there will be another which is known as FMEP. So, this is break mean effective pressure is equal to indicated mean effective pressure minus frictional mean effective pressure, that is very that is from the definition is coming. Okay. So, this is very important that mean effective pressure we can introduced. For this context I would like to say that the mean effective pressure is a good parameter and a good choice of the parameter for comparison of the engines, for comparing engines with regard to the design of the or output, because whenever you are comparing engines, so that means mean effective pressure is a good parameter for comparing the engine. Why? Because it is independent of the engine speed and size, right. So, if I use, so there might be a different parameter. So, I am writing now that there is a mean effective pressure MEP or mean effective pressure, or I can use torque or I can use power. So, these three quantities can be used to compare the engines, but mean effective pressure is a good parameter for comparing the engine because it does not depend on the engine size and engine speed. So, this is a good parameter for comparing engines with regard to design engine with respect to or with regard to output. So, we need to compare which engine gives better output. So, mean effective pressure is a good parameter for comparing engine with regard to output. Why? Because it does not, because mean effective pressure, because it does not depends upon the engine speed and size, because it does not depend on the engine speed and size. Suppose if I use torque as a comparing parameter, then a larger engine will have a better choice. On the other hand, if I use power as a comparing parameter, then speed become very important. So, if torque if I use as an engine parameter, then larger engine will be a good choice, larger engine will be always will be a good option or good choice. On the other hand, if I use power as an comparing parameter, then engine speed will be an important term, rather will be an important factor. So, that is why mean effective pressure is a good parameter for comparing engine with regard to the output, because it does not depend upon the engine speed and the size. On the other hand, if I can use torque and power as an comparing parameter, for that case we have to have that will be very much biased. That means, if a larger engine will be a good choice if I use torque as a comparing parameter. On the other hand, engine speed will be an important factor if I use power as a comparing parameter. So, from this point of view, mean effective pressure is always a good parameter, a good choice. Okay. Now, I will discuss about what is torque and power, because again we need to calculate torque. Torque is a good indicator of engine ability to do work, right. What is torque? Because this is the engine's ability to do work. So, what is torque? So, definition of torque is force acting at a moment distance. So, engine's ability to do work, and what is the definitions? Force acting at a moment distance. Force acting at a moment distance. So, if tau is the torque, then twice pi tau is equal to brake power Wb is equal to brake mean effective pressure divided by n, right. If tau is the torque, then 2 pi into tau is equal to brake power, brake work of 1 revolution. This is brake work for this is not a specific Wb, this brake work of 1 revolution this is brake work of 1 revolution, that is brake mean effective pressure into displacement volume Vd divided by n, where n is equal to number of strokes. Sorry, this is n is equal to number of revolution per cycle, number of revolution per cycle. So, brake work of 1 revolution, that is brake mean effective pressure into Vd by n, where n is equal to number of revolution per cycle. So, if it is a 4 stroke engine, that means tau is equal to brake mean effective pressure into Vd by twice pi into n. This is very important. Now, n is equal to 1 for 2 stroke engine, for 2 stroke cycle engine, for 2 stroke cycle engine, or n is equal to 2 for 4 stroke cycle engine. So, from there we can calculate easily torque. Now, what is power? Now, power we need to calculate torque and power, because what is the power output on the engine. So, power is essentially the rate of work of the engine. So, this is defined rate of work of the engine. So, this is the torque that is force acting at a moment distance. So, twice pi torque is equal to Wp brake work of one revolution, and that is brake mean effective pressure into Vd by n. N is the number of revolution per cycle. While you are calculating power, that is rate of work of the engine, and if I write W is equal to that is W dot. So, that will be equal to twice pi Nt, where n is equal to revolution, right. N is the engine speed. So, where tau torque. So, W dot is equal to twice pi Nt, or that is equivalent to n into n this is equal to W n by n. So, where n is equal to engine speed and tau is equal to torque. This is torque, n is equal to engine speed, or I can write in terms of W into rate of work of the engine, that is a power. So, from there I can calculate what will be the power output from the engine. So, with this I would like to move into the next part, that whatever I have discussed, that brake work essentially indicated work minus frictional work. We have calculated what is brake mean effective pressure, why it is so important. We have discussed that brake mean effective pressure is important from the perspective of this is very important because it is a good comparing parameter, it does not depend on the engine size and speed. So, if I use torque as a comparing parameter, probably a large engine would be a good choice. On the other hand, if I use power as a comparing parameter, probably speed might play a big role. So, from this point of view, it is always better to use mean effective pressure as a comparing parameter, because it is it does not depend on the engine size and the load. Fine. So, with this I would like to move to discuss about Otto cycle. So, I will take about Otto cycle. So, what is Otto cycle? As I said you that whenever we are talking about 4-stroke engine and 2-stroke engine, we have discussed in detail about 4 different strokes and 2 different strokes. So, normally we can't call it as a thermodynamic cycle, that is what also we have discussed, it is a mechanical cycle, but essentially you have seen that the pressure and temperature is continuously changing in a cycle. So, whenever we are discussing 4-stroke engine, we have seen that a piston movement is from BDC to TDC, coming back again, going there and coming back. So, the processes which is there, I mean inside the cylinder, we need to compare using an air standard cycle. So, a 4-stroke engine, a 4-stroke SI engine is compared with an air standard cycle which is known as Otto cycle. So, 4-stroke SI engine, 4-stroke SI engine is compared using an air standard cycle, because you need to compare, there is a continuous change in pressure and volume, we need to know the thermodynamic states at the end of each and every stroke. So, we need to map all those processes in a thermodynamic plane, and for that we need to compare all those processes using a cycle. And what is done, a 4-stroke SI engine is compared using an air standard cycle which is known as Otto cycle, which is known as Otto cycle. So, if I draw the PV and SI diagram, so again I have to draw the schematic of the engine cylinder. So, there is a top dead center, this is bottom dead center, and piston is having reciprocating motion, and reciprocating motion is converted to the rotary one using a crank and connecting nut mechanism. So, if I like to draw pressure and temperature in a thermodynamic plane, the PV plane, and then what are the processes. So, if I try to recall, intake process is occurring, probably I can we are approximating the pressure inside the cylinder is remaining constant, and if it is this is VBDC and this is VTDC, top dead center, bottom dead center. So, suppose when piston is coming from TDC to BDC during intake stroke, So, I am approximating this is this process 1 to 2 and it is occurring at constant pressure, that is atmospheric pressure inside the cylinder. This is an approximation. We will discuss that how good these approximations are, we will discuss one by one. So, piston is coming from TDC to BDC during indirect stroke and we are approximating that the pressure inside the cylinder is remaining constant, rather volume is changing from TDC to BDC, that is what we can see from the PV diagram, and pressure inside the cylinder is remaining constant and is approximated as atmospheric pressure. Fine. Next stroke is compression strokes. So, again piston will move from BDC to TDC. So, while piston is moving from BDC to TDC, volume will be compressed, the pressure will go high. So, pressure will be high, at the same time volume will decrease, and we are approximating this process by an isentropic process 2 to 3. So, this is process 1 to 2. Process 1 to 2 I am writing, rather I will write TS diagram, I will draw the temperature entropy diagram again, this is temperature entropy diagram. So, process 1 to 2 is the intake. So, constant pressure process, volume is changing. Process 2 to 3 is compression. So, this is constant pressure, this is compression stroke, this is we are approximating by an isentropic process, that pressure is continuously, pressure is also changing, volume is changed. So, 2 to 3 is an isentropic compression process where pressure is changed as well as volume decrease, pressure increases, volume decreases, fine. See, isentropic process again is an approximation, we will discuss that how good approximation this is, because we will have a continuous supply of heat from the engine cylinder. So, we will have a heat transfer, we cannot minimize the frictional loss to be a 0. So, if frictional effect is there, frictional loss is there, and we will have a continuous heat supply from the engine cylinder to the coolant, then whether this process is a this approximation is a good approximation or not, that we will discuss. So, 2 to 3 is a isentropic compression. Then whenever piston is reaching very close to the TDC, and then we switch on the spark plug and combustion takes place. Now, question is again, when there will be a combustion, there will be huge pressure generation and pressure will go high. So, this is 3 to 4 and sorry, this 3 to 4 is known as 3 to 4, this process is known as constant pressure heat addition. So, that means whenever piston is reaching at TDC, we need to switch on the spark plug to initiate combustion, combustion will complete, and as a result of combustion there will be a huge amount of heat generation, rather there will be a high pressure and temperature rise, and rather pressure rise and temperature rise, there will be high pressure. So, this process is this entire combustion process is we are approximating using a constant pressure heat addition process. So, as if we are adding heat Q in this process 3 to 4 is the combustion process and it is approximated as constant pressure heat addition. So, we are approximating pressure will remain constant and this is known as constant pressure heat addition. So, of course, piston will go to the TDC, combustion will take place and pressure will go high. Next stroke is piston is coming from TDC to BDC, of course, pressure will fall, volume will change. Here I would like to discuss another important point, that when you are approximating that the process 3 to 4 is a constant pressure heat addition process, that is whatever amount of heat is generated because of the combustion and there will be high pressure, and that we can see that from 3 to 4 pressure will be high and there will be huge amount of temperature rise, and that process is approximated by a constant pressure heat addition. Note that we are not thinking about a change in volume. So, we are thinking there should not be a change in volume, as if whenever piston is coming exactly at the TDC and whenever piston will be there at the TDC, by that time entire combustion will be completed, but this is not the case, because movement of the piston is very very continuous. I mean it is not possible that piston will go to TDC and it will wait over there for a few minutes, I mean for a few time, I mean maybe millisecond, of the order of millisecond, and by that time entire combustion will be completed. This is not the case. That means piston is coming to TDC, we are switching on the spark plug, and whatever time is required to complete the combustion, and for that duration piston will remain will remain at TDC, that is not the case, because the movement is very, the movement is continuous. We cannot stop the piston travel. But again, on the other hand, it is also true that we require a finite amount of time. Switching on the spark plug, complete of the entire combustion, it will take some finite amount of time, although of the order of millisecond. But still, during that time, it is not possible that the piston will remain over there exactly at the TDC. So how the volume will remain constant. So again, this is an approximation. We will discuss in detail about this issue. So this is a constant pressure heat addition. Now when piston is coming from TDC to BDC, so volume will decrease, pressure will fall, and that is again approximated. This 4 to 2, this is known as expansion, and it is known as, rather it is power stroke. This is power stroke in a 4-stroke engine, and this is approximated by constant pressure, rather isentropic expansion. Sorry, this is isentropic expansion. So we are approximating, this will be like this. So let us say 4 to 5, this is 5, and then 5 to 2 is exhaust. 5 to 2, that is piston again is coming from BDC to TDC. When piston is coming from 4 to 5 is the, 3 to 4 is a combustion process, that is the power stroke, and 5 to 2, 3 to 4 is combustion, there is constant pressure heat addition, this is power stroke, and while 4 to 5, whenever 4 to 5 is coming, this is power stroke, and 5 to 2 is exhaust. 5 to 2 is exhaust, that is it is approximated by constant pressure heat rejection. So 5 to 2 is a process which is exhaust process, which is approximated by a constant pressure heat rejection, and as if because of the exhaust, piston is coming from what? Piston and this is Q out, right. So 4 to 5 piston is coming from TDC to BDC, right. So it will there will be power stroke, and then 5 to 2 is exhaust, that is constant pressure heat rejection. This is not rejection, this is exhaust, that some amount of combustion product will go out, and because as I said you that this is not exactly exhaust, rather after power stroke, whenever piston is travelling near to BDC, we should open the exhaust valve. So some amount of exhaust combustion product will go out immediately after opening the exhaust valve. Why we are opening so? Because whenever piston has not reached even at BDC, you open the exhaust valve, intake valve is remaining closed. So we open exhaust valve to expel out a certain portion of the combustion product, so that when piston is coming from BDC to TDC during exhaust stroke, we will experience a relatively lesser resistance. So 5 to 2 is known as not exhaust, this is constant pressure heat rejection, because before piston coming at a BDC, we open the exhaust valve, some portion of the combustion product go out. So this is constant pressure heat rejection. Now process 2 to 1 is exhaust. This is exhaust, where piston will come from BDC to TDC, volume will decrease, and this process 2 to 1 is exhaust. So this is again constant pressure process. So we have approximated all the processes which are there in a 4-stroke engine, 4-stroke SI engine in a PV diagram, and the corresponding TS diagram will be like this, because 1 to 2, from 2 to 3, 2 to 3 is a process of isentropic compression. So entropy will remain same, we are assuming. Then 3 to 4 temperature will rise, this is constant pressure heat addition, and then this is 4, this is 3. 4 to 5 is again isentropic expansion, so temperature will fall, and 4 to 5, and 5 to 2 again this is constant pressure heat rejection, because some portion of the combustion product will go out even when piston has not reached at the BDC, because we open the exhaust valve. This is done only to reduce the resistance when piston is again coming back from BDC to TDC during exhaust stroke. So this is the TS diagram in a diagram in a TS plane. So 2 to 3 is the isentropic compression, 3 to 4 is constant pressure heat addition, that is mimicking the combustion process. Then 4 to 5 is the constant isentropic expansion, that temperature fall, and 5 to 2 is heat rejection, and that is what we have shown over here. So 2 to 3 and 4 to 5 entropy remaining same, so that is isentropic process, while 3 to 4 and 5 to 2 are the constant pressure heat rejection, heat addition and heat rejection process. So this is heat rejection Q out and this is heat addition Q in. So now we need to calculate what is the total work output from the engine and what is the heat supplied to the engine. From there we can quantify the thermodynamic efficiency of the cycle. So that part we will discuss in the next class. So far today I have discussed about the basic quantities that we need to know about the engine performance, that is work output, torque and power, and then we have introduced the concept of mean effective pressure, that is very important, that a good parameter for comparing the engine output as in regard to the engine performance in regard to the work output. And then we have discussed about why torque and power is they are not the good parameter for comparing the engine performance. Then we have discussed about Otto cycle. We have discussed that 4-stroke SI engine is compared using an air standard cycle which is known as Otto cycle. Then we have tried to map the processes which are there in a 4-stroke engine SI cycle, 4-stroke cycle SI engine in a PV plane. We have discussed about the intake, compression, combustion process, and then expansion and the exhaust in a PV and TS diagram. We have seen that we have approximated, but these approximations are not, whether these approximations are good approximations or bad approximation, that we will discuss systematically in our next lecture. And we have seen that the valve opening times are not exactly at the TDC or VDC, and there are a slight change. I mean we are delaying or we are opening earlier, and whenever we are opening valve when piston has not reached at VDC during during a power stroke, only to expel out certain amount of combustion product from the engine cylinder, so that when piston is coming from VDC to TDC during the next stroke, that is exhaust stroke, we will experience a relative rest resistance. Since certain amount of combustion product is going out, so we are having heat rejection from the system, and that is approximated by a constant pressure heat rejection in a PV diagram by process line 5 to 2. And these approximations are not very bad, that we will discuss in the next lecture. So with this I stop here today, and we will continue our discussion in the next lecture. Thank you.